So welcome to another segment of my physics videos. We are starting a new discussion called Introductory Electronics. So we are going to introduce you to electronics, but we are going to start with the cathode ray oscilloscope. Now, when we talk about a modern, cathode ray oscilloscope, it actually consists of a long evacuated tube with a filament and of course the cathode, just like you can see in the diagram. So the modern one, it actually consists of an evacuated tube. So the whole thing that you are seeing, it has actually been evacuated. So we can say it consists of an evacuated glass tube. So that is what you need to remember. Then it has got a filament, which we are calling as being F. So this portion that you are able to see there is what I'm calling as being the filament. So that is the filament. And of course, the filament is connected to a power supply. In this case, a 6-volt. It could either be AC or a DC power supply. Now, because this power supply of 6-volt, is sometimes called as being a low tension. So I'm just going to say LT. So that 6-volt supply can also be called as being a low tension. So my LT there, stands for what we are calling as being low tension because it is being supplied at a lower voltage. Then surrounding the filament is what we are calling as being the cathode. And remember, the cathode is actually negatively charged, and therefore it is connected to the negative terminal of the power supply, and approximately the voltage difference across them may be a 4000 volts. And the other side, on the far end of the filament, you have another metal plate. So the cathode is a metal plate but connected to the negative terminal, and also the anode is a metal plate but it is connected to the positive terminal, and therefore my anode represented by A there. So that is representing the anode there. So remember, the anode is positively charged while the cathode is actually negatively charged. And inside of this tube, the glass tube, air has actually been removed, and that is why we are calling it as being evacuated glass tube. Of course, this is my milliammeter that can be used to measure small amounts of current so that we see if there's any current that is going to be produced. Please just stay tuned so that I can get to explain about the modern cathode ray oscilloscope. So these are parts of a modern day cathode ray oscilloscope. So like I said, a modern cathode ray oscilloscope consists of one, it consists of a filament, and that is what I'm calling as being F there. Two, it also consists of what we are calling as being the cathode, and that is what I'm calling as being C. Then you're going to find that it contains what we are calling as being the anode, which is a capital letter A. Then of course, the whole part is actually evacuated, meaning that air is actually eliminated from this cathode ray oscilloscope. Like I said, if you look at the cathode ray, it is like a filament covered with a cylinder, and that covering that we are talking about is what we are simply calling as being the cathode. Of course, like I mentioned, the filament is connected. This filament is connected to a 6-volt. It could either be AC or DC power supply, and that 6-volt DC or AC power supply is also called as being a low tension. And of course, a potential difference of about 4000 volt is set up between the cathode and the anode. No wonder you are able to see that. But how does a modern cathode ray tube work? Well, what is going to happen is that initially the filament is heated by the current from the 6-volt or the low tension supply that you have. Then the filament in turn is going to heat up the cathode, which we have labeled as being our C there. So now, as the temperature of the cathode increases or rises, the thermal speed of the free electrons in the cathode, increases, and the electrons that are surrounding, that are contained in that metal, those free electrons that are contained in the cathode, escape from the atoms of the metal plate. And as the temperature of the metal actually increases, so the electrons are going to bow off. You can consider it like you have got a metal, and that metal is connected to a power supply. So if if this is a metal and the metal is heated to a high enough temperature, the free electrons in that metal are going to be ejected. So they are going to move, or we can say they are going to be bowed off. So when I say bowed off, I mean they simply escape from that metal surface. Now that process by which the free electrons escape or are bowed off from the metal plate when it is heated to a high enough temperature, that is what we call as being thermionic emission. So we can define an important term that you are going to be using in the exam. So you are going to be finding that, so we are calling it as being, thermionic. So thermionic emission. So we can say thermionic emission. So what exactly is thermionic emission? Well, thermionic emission, is the process by which, free electrons, so the process by which free electrons are emitted, from a hot metal surface. So that is what we call as being thermionic emission. So the process by which free electrons are emitted from a hot metal surface. So when free electrons are emitted from that hot metal surface because it has been heated, the process is what we are calling as being thermionic emission. Now I want you to understand that the emitted electrons. So let's imagine, let me just put the C there. So now once this metal plate is heated, you're going to find that free electrons are going to come out from that metal plate. Now because the anode is positively charged, you are going to find that the electrons will travel in a straight line and they'll be moving, they'll go in that direction, they'll get attracted to the anode. So those electrons will start moving from the cathode and they'll get attracted to what we are calling as being the anode. So those emitted electrons, we call them as being, thermions. Yeah, so I can put up a point and simply say, that the emitted electrons are called, so we call them as being, thermions. So that is what we call them, thermions. So thermions, I hope you're able to see that. Let me just write that one, my space is limited. So they are called thermions. All right, so that's the word there. So maybe if you're not able to see in that direction, this is the word thermions. So that is what we simply call. So the emitted electrons are simply called as being thermions. So that is what you need to remember in this discussion. Well, in this case, the milliammeter in the circuit, shows, the current. If at all it records a current there, it actually helps you to prove that the negatively charged electrons are moving from the cathode to the anode, because the circuit will be complete. So as the electrons are moving there, you are supposed to have a current in this milliammeter. So remember, that's a symbol small m and capital A, that is representing a milliammeter. So if you are able to record a current in the milliammeter, it simply tells you that indeed negatively charged electron. Remember, electrons are negatively charged. It simply means that they are moving from the cathode to the anode. Now one notable thing that you need to remember is that the movement of these free electrons, these electrons from the cathode to the anode, that is what we simply call as being cathode rays. So we are going to talk about what we are calling as being cathode, cathode rays. So they can ask you, what are cathode rays? So cathode rays, so these cathode ray, we can simply say, I will give you two definitions, you can pick up whichever you want. So cathode rays, you can simply say is the stream, so I can say is the stream of negatively, so is the stream of negatively, charged, fast, negatively charged, I can say fast moving, electrons. So that is what you can say if you want. So it is a stream. As you can see there, those are streams of fast moving electrons. So that is what we can simply call as being cathode rays. Or I can simply define cathode rays if I want, as cathode rays is the flow of electrons. So I can say it's the flow of electrons from the cathode to the anode. So that is what we mean. So my space is limited. So the flow of electrons from the cathode to the anode, that is also what we can call as being, cathode rays. So remember here, what is being created as the electrons are moving, you are creating what we call a beam of electrons. So a beam of electrons is actually going to be created. Now, the question that you may ask is that why is the glass tube evacuated? Why is it evacuated, or why should it be evacuated? So each time you need to connect it to a vacuum pump so that it can be evacuated. Why? The reason is very simple. You want all the air molecules to be removed, because if at all you do not remove air molecules in the glass tube, it simply means that the emitted electron are going to interfere. They are going to collide with the air molecules, and they will lose their energy, and they'll get re-attracted back to the cathode. As a result, this process of fermionic emission will not take place. In other words, you are going to reduce the effect of fermionic emission taking place. So please, you need to remember, this is just a cathode ray tube, a modern one that you are going to be seeing. Now, we need to talk about properties of cathode rays. Since we have defined cathode rays, let's conclude this discussion by looking at properties of cathode rays. So we can simply say, properties. So properties of cathode rays. So what are the properties of these cathode rays that we have talked about? Well, there are so many properties of these cathode rays, but I want to make this point clear again, is that the cathode ray is usually, so this cathode sometimes can be coated with the barium or strontium oxide. That is what you need to remember. So the cathode ray can be coated with either barium or strontium. Now this cathode ray, so before I can so the cathode is actually sometimes coated with what we call as being barium, or sometimes we can use what we call as being strontium oxides. So that is what you're going to find. Why? To give a copious, we can say, to give a copious supply of electrons. Now, what do I mean when I say to give a copious supply of electron? Well, when the metal plate, that metal plate that you saw, when that metal plate is coated with either barium or strontium oxides, you are going to find that there will be an abundance. It will help to produce an abundance of free electrons from that cathode. In other words, you just want to increase how many electrons are produced. So the surface may be coated with barium or strontium oxide. So let's come to now specifically to what we are calling as being properties of cathode rays. Remember, when we talk about cathode rays, like we said, they are negatively charged. That is what we know. So they are negatively charged. So we can simply say that they are negatively charged. So that is what you need to remember. So they are negatively charged because remember electrons are negative, so they are negatively charged. Another property that we can talk about is that cathode rays cause, we can say, fluorescence. So cathode rays cause fluorescence on a certain material. What do I mean when I say cathode rays, cause fluorescence on certain material? Well, what is going to happen is that once the cathode rays are produced by an electron gun, you are going to find that they are going to be accelerated by the anode. But when they fall on a fluorescence material, it simply means they are able to glow. In other words, they are able to produce a bright, if you don't want to say glow, they are able to produce a bright light. That's what we mean when they fall on what we are calling as being, especially fluorescent paints such as zinc sulfide or phosphor. So there are certain types of paints or materials that we talked about. For example, if you are using zinc sulfide or you are using what we call as being phosphor, you are going to find that when these electrons, the cathode ray, fall on such materials like zinc sulfide and phosphor, they fluorescence, they produce a bright, spot of light. That is what we mean. All right. Another property that we can simply give you is that cathode, rays travel. So cathode rays travel in they travel in straight line. Yeah, so in a vacuum, you're going to find that they're going to be traveling in a straight line. So that is what you need to remember. Now, in most cases, they travel in a straight line. Sometimes they have asked you this question in the exam where they bring up what we call a Morse cross. Yeah, so if between imagine that this is the cathode. So if between the cathode and what we are calling as being the anode. So let's say between the cathode and the anode. So this is the anode and you have what we are calling as being the cathode. If between maybe the cathode and the anode, let me just try to maybe shorten it there so that I can demonstrate what I want to demonstrate. So if at all, this is the anode, and this whole thing is enclosed. You have a screen somewhere there. You do have maybe a screen somewhere there. So imagine that it is evacuated. You have actually enclosed it in some sort of a tube. And you put up some more like what we call as being a Morse cross. You put up what we call as being, a Morse, you can say a Morse cross, made of aluminium. If electrons are produced here, remember this whole thing is actually, it is actually opaque, meaning light cannot pass through. So you should be able to see a shadow on the screen. So you should be able to see an exact shadow. So this is going to be a shadow that is going to be cast on this thing we are calling as being the screen. So that is what is going to happen. So as the electrons are moving there, because this is opaque, they will not pass through. So as a result, a shadow is going to be cast on the screen. So this is how we can tell that cathode rays travel in a straight line. So that is what you need to remember. Okay, let's give you a few properties just to conclude up this discussion. Maybe the fourth one that I can tell you is that cathode rays, travel with a high, so they travel with a high speed, and we can simply say possess a lot of kinetic energy. Now, it is possible that you can find the kinetic energy that the electrons possess. Of course, if you are doing pure sciences, you need to remember that voltage is equal to work done divided by charge, and therefore work done is equal to voltage times charge. But of course, we can replace our we can replace our charge there by electron, where in this case E is the charge of an electron. So that E is representing the charge of an electron. We know what is the charge of an electron. So work is equal to E, the charge of an electron, multiplied by voltage. But remember, work is a form of energy, and therefore we can come up with the equation and say since work is a form of energy, energy is given, in this case we are talking about, since work is a form of energy, the energy we are talking about is kinetic energy. So we can say the formula can reduce to half mv squared is equal to EV. So it is possible for you to know, it is possible for you to know the speed of what we are calling as being, the electron by applying this formula. That is if you are doing pure sciences. Please, if you are not doing pure sciences, you just need to know the property that is there. All right, so that is what we are talking about there. So remember that the speed of an electron can actually be, found. Yeah, so what you can do, the speed can be increased by increasing what we are calling as being, the potential difference between the electrodes, the cathode and the anode, and hence you can find, the speed. Let's look at another property that we can talk about there. We can simply say that, cathode rays, because they are negatively charged, so we can say cathode, ray can ionize. So they can ionize gas. They can ionize, maybe we can say the gas, through, they can ionize the gas through which, they travel. So please get to know that. Let me just give you a few. Another property that we can talk about for cathode rays is that, this is going to be number 6. We can simply say that they are deflected. So we can simply say that cathode rays are deflected. So cathode rays are deflected in an electric field. So if cathode rays pass in an electric field, they are going to be deflected, they are going to bend. It is possible. Another property that we can say is that cathode rays are deflected. Again, they can be deflected in a magnetic in a magnetic field. Remember, because they are negatively charged, no wonder they can be deflected in an electric field as well as in my magnetic field. The last property that I can give you is that cathode rays, affect what we call as being photographic papers. In other words, they are capable of also blackening what we are calling as being, photographic papers. So when cathode rays are incident on a photographic paper in a dark room, the paper gets, so if it's in a dark, you're going to find that the paper gets forged. So that is what is going to happen. So these are some and many other properties. I don't mean they are the only properties. You can look out for other properties. Please watch out in my next video as we try to talk about now the cathode ray oscilloscope. How this guy, the cathode ray tube, is now amplified into a cathode ray oscilloscope. Please, you can subscribe so that you can receive more videos in case I produce new ones. Thank you.